Ngā mihi nui kia koutou katoa. I'm Dr. Jackie Tran and I work as a researcher at High Performance Sport New Zealand. Welcome to part 2 of the session on research tools. Before we hear from the speakers, a few notes. As you have been doing throughout the conference so far, please post your questions in the live Q&A box, which is on the right side of your screen. And if you have any technical difficulties, you can go to the live support button, which is in the top right corner of your screen. For this part 2 of session 5, we have 2 presentations, and then we're going to break for lunch at 1:10 p.m. Our first speaker is Eric Burgueno, who will be presenting on practical recipe standards for Singularity containers to make life easier for data scientists. Over to you, Eric.
Right. Hi, everyone. Hopefully you can all see my screen now. So in this demo, I'm going to show you some of the standards that we adopted for the recipes of our containers that we deploy in PowerPlant, which is Plant and Food Research HPC cluster. Now, the reason we adopted some of these standards is to try and make life easier, not only for myself as the admin, but also for the data scientists themselves. One of my goal tenets is to try and make technology as transparent as possible to the end user so that they can focus on the science. And ideally, in the context of containers, that means that they shouldn't even know the fact that they're running containers in the first place. So let's have a look at how we can achieve that through some of these standards that we adopted. Now, when you think about containers, you're probably thinking about Docker. Hopefully, you all know about Singularity. I'm not going to cover the differences between the two. Shameless self-promotion here, but I already did this a 10-minute talk last year at Linux Conference Australia. You can have a quick look at that talk later on if you want to know why do we prefer Singularity over Docker in HPC contexts. We can see your Zoom. Okay, sorry, let me move that away. Hopefully that's better. Thank you for that. So if you want to know the differences between the two, there's a link to a YouTube video. You can have a look at that. We're going to focus on Singularity for this demo today. Now, if you have never seen a recipe file for a Singularity container, also called a definition file, this is a very minimal example of what one might look like. We have a bootstrap section that tells Singularity how to start creating the container image that you want. In this case, we're starting off from a Docker image that it gets pulled from Docker Hub, an Ubuntu Bionic container. Next, we have a label section that includes all of the metadata that we want to add to the container image. And there are no limits as to how many labels you can attach. They're really useful to provide information about the container image to the end users of that image. Next, we have a post section, which is where we document all of the commands that are required to install and configure the software that is provided inside a container image. And finally, we have a run script section, which tells Singularity what's going to happen or what should happen when the user runs the container image for the first time. Now, there are obviously more sections than this one. These are just the ones that I will focus for on this demo today, and the ones that we apply the best practices that we adopted. I did say that this is a demo, so I'm going to stop boring you with the slides now and switch over to a Jupyter notebook that I have prepared. And the reason I'm using Jupyter is because it saves me from doing a lot of typing, so I'm just going to use this instead. Now, the first thing that I want to talk about is the bootstraps. As I mentioned before, this tells Singularity how are we going to start creating our container image. We decided to use Docker images provided in Docker Hub by default, and there's two reasons for this. One is that the images that Docker Hub provide seem to be very widely used. They have a lot of exposure, and particularly the ones that are created by the distribution maintainers are the ones that get the official support. But Docker is not the only bootstrap that you can use. You can also use a YAM repository or an Debian package repository. You can also bootstrap from a different Singularity image. The main message or the main takeaway when it comes to choosing a bootstrap is to make sure that you understand what the provenance of your base image is and that you choose the base images wisely. Particularly for the images that we create, we tend to prefer, if it exists, the Docker image in Docker Hub that the upstream authors tend to provide. In this case, we're just grabbing the Amazon image for the AWS CLI tool. But if none exist, then if we have to compile everything from scratch, we start off from preferably a long-term support version of some Linux distribution of our choice. Now, the next section that I wanted to briefly touch base on is this label section. It's very important to include as much metadata as possible inside the container images that you create, primarily because if the researcher distributes that container image elsewhere, you want other people to be able to inspect it and quickly see what the image is all about. At the very least, we require that all of our images have a maintainer label with some point of contact that users can go to in case they want to ask questions about how the image was pulled together. And in this case, a version tag that specifies what version of the software we're providing inside a container image. Moving on to the post section, one of the most important things that we want to ensure when we install software inside a container image is to make sure that the versions of the software that we include are tagged to a specific point in time. The reason behind it is that you may put the recipe in a Git repo and just publish it on GitHub or some other VCS GUI, but if the image file itself is distributed and gets either corrupted in transit or you have to rebuild it for whatever reason, if you didn't version tag the software that gets installed inside a container image, you might end up with conflicting dependencies or dependencies that don't work well together. So you need to be careful about not blindly download the latest version of the software that's published and try and version tag every single thing that you put in the image. And there are a few strategies that you can use to ensure that that's the case. The first one is to simply grab whatever version is available of the tool that you're installing from the distribution repositories. In this example, I'm installing the Abyss tool, which I'm just grabbing from the Ubuntu Bionic container image. And the version that comes from the repos through a simple apt-get is the version 2.02. If I wanted to grab 2.10 instead, I will just switch my base image to Ubuntu Cosmic because that's what version is provided on that distribution. Same for 2.15, I'll just go into Ubuntu Disco. The reason this is sort of, I think, the exception or the lazy way of going around it is that there may be very minor changes to the versions that are provided in these repositories, but they tend to be somewhat stable. So I think it's okay to just rely on that and just use those. But if they're not available in the distribution repositories, more often than not, you have to download the source code and compile it yourself. Hopefully that's in a version tag tarball that you can simply curl directly into your container image, and then you don't have to worry about the version because you're always going to download that specific release. But I've seen a few cases where that's not what happens. You may have tools like HTSlib that are version tagged, but they're not released as tarballs. So you have to clone the repository and then reset or change the specific branch that has the release that you want. Or if the author is using Git tags, then you can simply reset the repository to the specific tag that you're after that includes the version that you want. Last but not least, in the somewhat common scenario where the author doesn't version tag at all and simply bumps the version every time that they feel like it, another strategy that you can use is to simply clone the repo and then check out the specific git commit hash at the point of build time and make that part of your container recipe just to make sure that if you have to rebuild it again, you'll end up potentially with the same versions inside. Now, this isn't going to make the recipes themselves deterministic. Anything can happen. The author may decide that they no longer like GitHub and they want to move to GitLab. So this doesn't guarantee that the recipe will always produce the same container image, but it does increase the chances of that happening. Now, moving on to the run script section. If you're going to take away anything from the session, I want this to be it. I mentioned at the beginning that we want to make life simpler for data scientists to the point that ideally they wouldn't even have to think about the fact that they're running Singularity or Docker or any container runtime whilst they do their science. And the way that we achieve this is through the entry point. You may be aware that Singularity images are effectively a single file that exists in the file system, and that those images can be made executable directly as if they were a single binary blob. The way to achieve that is through the run script section in the Singularity recipe. This is the equivalent of, in Docker lingo, what the entry point or the CMD directives achieve. In this case, we're telling Singularity that if the image file gets run or if it's executed directly, which are equivalent, the container is going to run Tomahawk and any command line arguments that go after that. Now, this is a very simple strategy that allows you to, for example, call the Singularity image file simply as Tomahawk, and then you just add that to the user path through environment modules or some other way, and the user will not know the difference between a Tomahawk installation done natively on the HPC machine or one that's running inside a Singularity container. But more often than not, you have to deal with software that do not provide a single binary. So then this syntax here is impossible to apply. I took inspiration from BusyBox, which is a big binary blob that implements very common Linux tools inside a single binary. And one cool feature about BusyBox is that you can call that binary, the file, you can rename it into any of the functions that it provides. And then when you execute it, it will actually provide that functionality instead of having to call BusyBox and then the name of the function. So in order to achieve the same effect in a Singularity recipe, we can use a run script that leverages the Singularity _name environment variable. In this case, I decided to wrap that around an if block that simply checks if that name is available inside a container image, in this case in user local bin, but it can be anywhere else. And if not, print out a help message so that the user know what commands are available to run inside this container image. The cool thing that you can do once you have your run script this way is to have a directory with the container image available, and then you can simply either rename or create symlinks or hard links pointing to the container image with the names of the binaries that you want to make available to the end user. So if you add this path to the path environment variable of the end users, then by them running the image file directly, they will have a help message that tells them the full syntax for how to run or how to use the container image. But if they're instead calling one, as they will probably expect, one of the symlinks, they will get a different behavior based on the name of the actual symlink that they're calling. So here you can see me running the help message for Polish clusters and cluster GFF. And as you can see up here, they're simply symlinks pointing to the container image. This is very useful again because you can do all sorts of things with the module files. For example, if you need to bind mount different paths in your HPC file system inside the containers for the containers to work, you can do all of that through the module files, and then everything is transparent to the user. They don't even need to know that they're dealing with containers. Specifically, another strategy that we decided to adopt is for those tools that require read-only data to be available to do, for example, comparisons against the data that the user wants to do. Squeeze meta is one of those examples. The problem with including read-only data or data that doesn't really change that often inside a container images is that it will make the images really large. And if you have to do multiple versions of the same container image, then you're duplicating all of the data multiple times. So we took a more pragmatic approach and directly downloaded all of those databases or raw data in our HPC file system, and then bind mount that on runtime instead of including that information or those files inside a container image itself. Bonus points if you can do that through the module files. You can simply prepend the path to the raw data, whatever it is in your file system, through the Singularity bind path variable. And as you can see, I'm just prepending the location of the data that Squeeze Meta expects at runtime. So if I just load it and then I echo that variable and then run an ls on the host or inside the file system, I just get the same result. Now, last but not least, another strategy that I adopted from the Docker best practices is to clean up after myself, which helps reduce the total size of the images that we create. One very cool thing that Singularity adopted in version 3.2 is this notion of multi-stage builds, which basically means that you're creating a temporary container with all of the compilation tools that are required to build your application or your software. But then you create another container that's empty, and you simply copy the build artifacts or the compile binaries into that image. So the final image that you provide to the user does not include any of the compilation or build time dependencies like GCC, make, or wget. In this example recipe, I am downloading Hammer and doing the .configure, make, install. And for doing those, I need both GCC, make, and wget to get the source code. But none of those are required to run the software. So then the final image simply copies the statically compiled binaries or the fully compiled binaries and then provides the run script as before. If you cannot use multi-stage builds for whatever reason, you can simply just do a cleanup section and remove those dependencies. It won't be as clean. And in this case, these dependencies don't really take that much space, but it's always useful to just have it. So,
all right, Eric, I'm just going to jump in there and thank you so much. We have a couple of questions coming through,
cool.
So we'll spend a couple of minutes answering those. So first question is from Joel. We've got two questions from Joel. Have you looked at using the universal base image as a base image?
I have. The reason we sort of started relying on Docker was because the UBI wasn't available when we started using Singularity. We haven't gone back and revisited a decision, but we can always do.
Great, and we've got a second question from Joel. This appears to be a lot of coding what things like OpenShift and Kubernetes provide as standardized API or pipeline calls. What advantages are you gaining by doing it yourself?
Well, for starters, most of the OpenShift and Kubernetes stack relies on primarily Docker. There is a runtime available for using Singularity as well inside an OpenShift or Kubernetes cluster. We haven't had a chance to unify what seems to be these two different worlds, Kubernetes and HPC yet, but it's definitely something that we're looking at in the pipeline. So yeah, watch this space, I guess.
Great, thanks for that, Eric. We've got a couple more minutes before we will shift over to our next presentation. Do you have any final words that you want to leave us with?
Very quickly, just as a summary, choose the bootstraps wisely, use labels, be strict about the versions, define good entry points, try not to include raw data in the container image if you can avoid it, and clean up after yourself. That's a very brief summary of what we covered. All of the best practices that we documented and some of the recipes that we use to create containers in our HPC are available in github.com/powerplant. Everything is in a mid license, so feel free to go and do whatever you want with it. And obviously, we accept pull requests and suggestions. Obviously, feel free to contact me if you have any more questions after the talk.
Great, thank you so much, Eric. So if there are further questions, the live Q&A box will still be running during the session. So feel free to drop in any further questions that might come to mind for you from Eric's presentation, and he can also respond in text in the platform. So we will switch over now to our next presentation, which will be from Marko Laban and Chris Scott, who will be presenting on running web applications on HPC using containers. Over to you both.
Hello.
Thanks. I'll just share my screen. Hopefully you can see that okay?
Yep.
Over to you, Marko.
Okay, so maybe go on to the first slide, please. Okay, so what problem are we trying to solve? Basically, hosting public-facing web apps in the modern cloud environment is these days ubiquitous. So, but it's not so common in an HPC environment. We know it's easy to do this in the cloud because the infrastructure was designed to support this concept at large scale from the very beginning. There is a huge community of practice and big ecosystem of tools, and there are even movements like DevOps that provide a lot of support for people who want to host web applications. and there is also a standard service. It is a standard service that is fully supported by the commercial operators. On the other hand, it's still, from our experience, a bit hard to do for researchers on an HPC because there is currently no standard HPC-specific tooling or a set of workflows or first-class support to do this job. So usually a researcher needs to roll their own solution. Also, the HPC system architecture is rarely designed to specifically cater or support a scenario of exposing web apps to the outside world. And security, availability, maintainability, and complexity are currently challenging still. Next slide, please. And then basically we can ask ourselves, who needs this? Because why would anyone bother at all to expose web apps on HPC when it's much easier and almost free to do so in the cloud? I guess web apps themselves provide an easy way to submit jobs and access job results on HPC, and this extends the audience for, let's say, an experiment or an analysis tool that requires a lot of CPU or memory or GPU, or it may have some specific data sovereignty needs. If you wanted to do this in the commercial cloud, this would probably be way too costly, or you would encounter issues with the geolocation of the data because your data would be hosted somewhere where the public cloud provider data center resides. Next slide. So for our solution, basically we had a specific use case, and our aim was really to use the set of available tools to deliver the solution in a timely manner. We couldn't do much about changing how the infrastructure was set up. We pretty much focused on exposing the app, and there basically we leveraged containers in Singularity. It is indirectly run by Jupyter Hub, and then basically it's Slurm. The Slurm job runs the Jupyter single user server process, which has the Singularity container. And within the Singularity container, we have bundled the RCompute scripts, which is the core that does the calculation. And then we've basically also bundled a Apache web server that hosts the web app, and through Jupyter server proxy via Jupyter Hub, this was exposed to the outside world. Also to mention basically the files that the results of the computation are hosted on GPFS, and these are mounted inside the Singularity container for computation, and as well for the web server is serving these to the same channel. Over to you, Chris.
Thanks, Marko. Yeah, so for the next few slides, I'm just going to do a bit more information about the specific use case that we worked on a researcher with on this project. So we worked with Basharat Bhatt, who's a researcher with Genomics Aotearoa, and he's working to develop a web app for running this EWAS pipeline. So his idea is he wants to make it as simple as possible for researchers to upload data, to run his pipeline, and to view the results. And that's why he's created this web app. One of the challenges Basharat faces, though, is that in order to run this EWAS pipeline, it requires many hundreds of gigabytes of memory, depending on the sample size that's being uploaded. So that really means that you can't really use a desktop machine, or it might be very costly to use the cloud. But on NeSI, we can support this type of workload because we have big memory nodes. So as Marko already mentioned, we looked at creating Docker and Singularity images to run this web app to make it portable. All the development was done on GitHub for this project. And then we looked into the options for how we can actually run this web app on NeSI. I should also mention that this work was done through NeSI's consultancy service. So we have a team of research software engineers and data science engineers who are available to work with researchers around New Zealand. So please do get in touch with us if you're interested to find out more about that service and how we can help you. Anyway, the initial solution we came up with for the researcher before we had the Jupyter solution available was SSH based, because it used to be that SSH was the only way you could access the NeSI machines. For this solution, the researchers would need to SSH into the cluster. They'd have to navigate around the command line, edit some Slurm scripts to request the resources that they need. They'd have to pick a port and hope that nobody else was using that port on the same machine their job was going to run on. And then they'd have to submit the job and wait for it to start. And after doing all this, they'd also have to set up an SSH tunnel from their machine to the cluster so that they can actually run the web app. And when we presented this solution to Basharat, we could see that it wasn't really what he was hoping for, or what he was hoping his researchers would have to, the experience his researchers were going to have that were going to use his web app. Fortunately, around that time, NeSI's also just released its Jupyter service on the cluster. So we're in the early access phase now where researchers can try out running, Jupyter notebooks on the cluster. And the way this works is people go to the jupyter.nesi website. When they get there, they can request resources such as memory and wall time and so on. And then when they launch their Jupyter notebook or Jupyter service, they get into Jupyter Lab. And from within Jupyter Lab, we can make it so that we can add an extra button in there, which is the EWASP button, which will launch the web app, and then the web app runs within the resources that were requested on the previous page. So this is a completely browser-based solution. There's no SSH, no terminal, no command line, and this is really much closer to the solution Basharat was hoping for his web app. So I could quickly do a little demo just to show you kind of what this looks like. So when a researcher goes into Jupyter Hub on NeSI, this is the screen that they get presented with. So they can choose a few basic options here, like what project, how much wall time they need, how much memory, and whether they want a GPU. They can then click the start button and they'll end up going through to Jupyter Lab. And for those that are familiar with Jupyter Lab, you'll see that you've got the normal kernels like Python and R kernels that you can use to launch to launch notebooks. But there's also this EWASP button, and if we click this button, it's going to launch the web app that Basharat's developed. And how we get that button to show up there, there's a little bit of configuration required for this Jupyter server proxy. So you can see we just have to add into the Jupyter notebook config these few lines, which you've got the EWASP, which is what shows up in the button, and then it basically telling Jupyter what command to run when that button gets clicked. So here we have a script which just launches the web app running in the Singularity container, and the web app just takes a couple of arguments. One of the arguments is the port, which when someone clicks that button, Jupyter Lab is going to have a look to see what available ports there are, and it'll fill us in with a port number. So the researcher doesn't need to worry about that, and it'll also pass in a base URL argument. And that means that when the researcher then clicks this button, it's just going to fire up their web app, and the researcher is then free to go around and do run their pipeline and get their results. And it's all web-based, so that's a really nice way to access the large amount of resources we have on NeSI. So I think that was all of the demo from me. So I'll hand back over to you, Marko.
Okay, so basically, maybe we go a bit in more detail on how we've done this. We obviously use containers because this enables easy sharing of the application code across different facilities. Otherwise, people have to copy and install the apps, and this way there's just one image that needs to be communicated. It bundles all the necessary files required to run, including the PowerScripts. scripts. We've built first a Docker image, and then we've built a Singularity image from that Docker image. So basically, even if someone wants to host this in public cloud, they could do that with the Docker. We've mapped the data from HPC file system using the standard container methods. And we've applied various hacks in the application itself to actually enable this interesting way of serving through a tunnel or proxy. One issue is relative paths won't work out of the box because the exposed path is different than the path that the app itself thinks it's running under. Over to Chris.
Yeah, so with the Jupyter server proxy, what this proxy allows you to do is to proxy to any arbitrary server running somewhere on the cluster. It's really nice. It can be some server that's running on the same node as the Jupyter lab, or it can be on a different node somewhere else in the cluster. It also gives you the options to start and manage the process. But the other option is that you could start the process separately and then just proxy to it. And this probably isn't the ideal solution for running a web app on the HPC, but it's a good workaround for being able to expose services to the outside world when there's nothing better. There's no other better way to do it. So I think back to you, Marko.
Yeah, thanks. So basically, doing all this wasn't without challenges. Well, the first biggest challenge is can't use Docker on HPC and probably won't be able to do so for some time ahead. But I guess in the process of converting the Docker image to a Singularity image, we found quite a few instances of Docker containers being used to being able to run as root. So people just do things that require privileged access, and then when we need to have a Singularity image built out of it, we need to work around these things that require privileged access available to Docker. Obviously, it can't be exposed to the outside world easily, so we spent quite a bit of time figuring out the tunneling and ended up with having Jupyter solution. There is also, our app is running on a scheduler queuing system, which is classic HPC. Slurm, it's not ideal for interactive use because at times when there are peaks, user may have to wait for resources. So it's a little bit hard to get the real-time interactivity sometimes. And of course, there are some complications on deploying the solution and using it. You can't build the containers on HPC easily. So usually we would build locally or in the cloud and transfer to the cluster. Many R packages need to be built from source, and then rebuilding the Docker images, especially when you're trying to figure things out, it takes quite a long time. And I guess I've already mentioned the issue of our routing paths. Over to you, Chris.
I think that was all we had really. But we're happy to take any questions people have about the talk, unless you wanted to finish off with anything, Marko.
All right, we'll swing into questions. Thanks so much, Chris and Marko, and I'll tip my proverbial hat to you for the dual presenter method, which is pretty smooth actually, so good job. So the first question is from James. How large are the data collections that researchers would be supplying to use with eWASP? If they are large, how do people handle uploading those to NeSI?
It's a good question, and we're probably not in the best place to answer because probably Basharat would be a better person. I mean, my understanding is that it could probably in the gigabytes range of data to upload. So, you know, there's a couple of options on NeSI for uploading the data. One is you could do it through the actual web app, which might be a bit slow for big data sets. The other service we have on NeSI for transferring large amounts of data is Globus, which is also web-based. So there's a possibility that, you know, researchers, if they had really large amounts of data, could upload the data using Globus onto the file system, and then they could just select that directory from the web app rather than uploading it through the browser.
And I guess it's worthwhile mentioning that the bottleneck really is memory used during the processing time, so the data set won't be that huge, but the memory requirements would be quite huge.
Great, thanks. And we've got a second question here from Joel. How have you looked at using source to image pipelines so that you are not tied to specific CRI runtime and image format?
I'll try to answer that. No, we haven't. And I guess this app is still early in the development lifecycle, so we've almost just figured out how to do this. So probably we will get to it a bit later in the cycle.
Fantastic, thanks, Marko. So we've still got a bit of time if there are more questions from the crowd. So feel free to use the live Q&A feature in your platform to do that if you like. While we allow a bit of time for that, we'll be heading into lunch shortly, and once we come back from lunch, the conference program will resume at 2 o'clock with lightning talks. So I'll just hold on for a couple more seconds to see if there are any further questions for Marko and Chris. Okay, it looks like there aren't any further questions for the time being. If you do think of anything further and you'd like to get in touch with Chris, Marko, or Eric from this session, you can connect with them in the meeting hub or through their emails, which are accessible through the book of abstracts. So thank you again so much to the presenters, and we'll see you all at 2 o'clock. Hi, Dada.